Okay, let's get started with the evolution and death of low-mass stars. When we think about the cool, red, smaller main sequence stars, we're talking about stars called red dwarfs. The cores of these stars have temperatures and pressures that are relatively low, resulting in the extremely slow rate of thermonuclear fusion. Hydrogen is being fused into helium in the core, sure, but very, very slowly. These stars are also considered fully convective, meaning the only other layer within their internal structures is a convection zone directly surrounding their cores. Here we can see a diagram showing exactly that for a very low mass star, one that's only 10% of the sun's own mass. The inner region, the core where nuclear fusion is happening, is represented by the paler yellow circle, and the convection zone, just outside it, where hotter plasma rises to the surface of the star while cooler plasma material sinks inwards, is represented by the thicker red ring. Let's see what's going on inside this low-mass star. Even the lowest mass stars that are considered main sequence stars are fusing hydrogen into helium in their cores. The helium produced in the core convects outwards in these low-mass stars, allowing for more of the hydrogen in the star to fall inwards towards the core, where it too can fuse into helium. Eventually, all of the hydrogen in the star is fused into helium, which over time turns the star into a ball of helium as it runs out of hydrogen to fuse. Once the hydrogen is depleted, there is no more radiation pressure pushing out from the core of the star to balance against the star's weight, so the star collapses inwards. The temperature in the core rises as a result of this, but it never reaches the necessary temperature to kickstart helium fusion, which is 100 million Kelvin. Remember, the core of the star would have continued fusing the present elements into heavier and heavier elements if it could, if it had the right temperature and pressure combination, but in this case it doesn't. So this remnant dead star is small and hot, and we call it a white dwarf. Now, white dwarfs, at least the ones that are formed from low-mass stars specifically, are small, hot spheres of helium. They will eventually cool down and fade as time progresses, but there aren't any of these pure helium white dwarf stars just yet. The universe just doesn't have any yet. This is because the low-mass stars that will eventually turn into these pure helium white dwarfs haven't actually evolved yet. But why is that? Because these low-mass stars are still going strong on the main sequence. Even those that formed right after the Big Bang still have a long, long ways to go before they even start evolving. But once they do, we can track the changes in their characteristics by repeatedly plotting them on the HR diagram and seeing them move off the main sequence as they evolve. Once they've used up all of their hydrogen, they'll appear at the rightmost edge of the main sequence, and from there they'll begin their evolutionary tracks all around the HR diagram. These red dwarf stars will grow hotter, but dimmer as they grow smaller and older, and eventually cool down and fade in brightness some more as they become white dwarf stars. And with that, they'll have evolved and reached the end of their lives.